Hello everyone, welcome back to Native Engineering. We are doing another question on stress and strain, and the question reads as follows. Figure 1.11 shows a round steel bar consisting of three different diameters. The maximum stress in the rod is 75 megapascal and we are given the Young's modulus as 200 gigapascal. And then the questions they say, calculate the diameter of the middle portion. And then number 2, they say, calculate the total length of the rod if the total change in length is 0.3 millimeters. So looking at the diagram, figure 1.11 that we are given, we have a force that is applied, a force of 100 kilonewtons, and then we are having three sections. We have the first portion with a diameter of 60, a length of 100. We have the second portion, we're not given the diameter, and we are given the length as L. We are not given the length, in other words. We have the third portion. We are given a diameter of 80 and a length of 150. So in the information they gave us the maximum stress. Looking at the diagram, where will you say the maximum stress will occur on this steel bar? It will occur on the portion with a minimum diameter, because minimum diameter will mean the minimum area of the tree, and the smaller the area, we know the larger the stress will be, meaning the maximum stress will occur on the middle portion. So let's look at the questions. They say, question number 1, calculate the diameter of the middle portion. We already know that the maximum stress being 75 is going to occur on the middle portion, and we know that the stress is given by force divided by area. We have the force. The area we do not have because we do not have the diameter. We have the stress, but the area we do not have because that is exactly what we're trying to calculate. So we're going to make the area the subject of the formula, which will give us force divided by stress. And then we substitute 100 times 10 to the power 3 divided by 75 times 10 to the power 6. This will give us an area of 0.00133 meters squared. And then from here, because we are not looking for the area, we are looking for the diameter. We know that area is given by pi divided by 4 d squared. That is our area. So we are going to, let me erase this, use that formula to get the diameter. We have the area pi 4. The only unknown that we do not have is the diameter that we're looking for. Therefore, we're going to say diameter squared, it's equals to the area being 0.00133 times 4 divided by pi. And we're going to put a square root. This will cancel here, and then we're left with d. Our diameter, I got it as 41.151 times 10 to the power -3 meters, or you can just put it as 41.151 millimeters. And then we go to the second question. They say the total length of the road if the total change in length is 0.3 millimeters. So we're going to do this. They are looking for the total length. We know the total length is given by length number 1 plus length m, which is the middle section, and then length number 3. We have this one, we have this one, we do not have this one. So to get length number 3, length m, which the length of the middle section, we are going to use the formula of elasticity, Young modulus of elasticity, which is stress L, which is the length that we're looking for, x m. But we do not have this one. We are given the total change in length as 0.3 millimeters. So we can use this to get this. And then from this formula, we are going to get the length. From there, we are going to calculate for the total length. So we're going to start with finding the change in length of the middle section. Total change in length is equal to change in length number 1 plus change in length of the middle section plus change in length number 3. This one we can calculate. This one, change in length number 1 and change in length number 3, we can calculate. We have all the information to calculate those two. The formula that we are going to use to calculate them is x, it's equals to f. We have force, we have their lengths, we have their areas, and we have the Young modulus of elasticity. Since we are dealing with the same material and we're given the Young modulus of elasticity, so we're going to start with that. X1, change in length number 1. F, L, A, E. 100 times 10 to the power 3. That's our force. Our length, 0.1. Our area, 200 times 10 to the power 9. That's our Young modulus of elasticity. I got our answer here is 0.17 times 10 to the power -4. I'm going to express this in millimeters because the change in length that we are given, it's in millimeters. So you can do it either way. You can either change the total change in length to meters, or you can change these values to millimeters. So in this case, I'm going to change this to millimeters, and it's going to be 0.0179 millimeters. Which one you change doesn't really matter. We are going to get the same answer. And then from here, I'm going to get change in length number 3. Change in length number 3, it's equals to, still same formula. The force is the same. What is the length? It's 0.15. It's just 150. It's the same thing. And then the area divided by 4 times 0.08 to the power 2 times the Young modulus of elasticity, which is 200 times 10 to the power 9. And then we are going to get an answer of 0.149 times 10 to the power -4. I am also expressing this in terms in millimeters, converting it to millimeters. Millimeters. So now we are having something like this. Go back to our change in length, total change in length. It's equals to change in length number 1 plus change in length m plus change in length number 3. Our change in length is 0,3. This one we are given on the equation. And then our change in length number 1, we calculated and got it as 0.0179 plus xm plus 0.0149. And then from here, our change in length number m is 0.3 minus 0.0179 minus 0.0149, which will give us our change in length as 0.267 millimeters. We are not done. Remember, we are looking for the total change in length. So from here, we are going to continue to get the length of the middle section. Just erase this. So we are going to say the Young's modulus of elasticity is given by stress length divided by change in length. We're dealing with m, so we're looking for xm, lm. We have this and we have this. This will be our maximum stress which we are given. So from here, we're going to make this the subject of the formula, and it is Young's modulus times xm divided by the stress, which will be the maximum stress. Then we substitute. Our E is 200 times 10 to the power 9. Our change in length for m, it's 0,267. And then our stress is 75 times 10 to the power 6. And then this will give us a length of what? Of 712 millimeters. Our total change in length, therefore, is 0, it's in millimeters. So it's going to be 100 for the first section, and then the second section number m will be 712 plus 150, giving us a total answer of, giving us a total answer of 962 millimeters. So whether you put this in millimeters or in meters, it's up to you, unless stated that you must leave the answer in millimeters or in meters. If that's what they say, then you must leave it in, you must give it the SI unit that they asked for. In this case, they didn't say, so I'm choosing to leave it in millimeters. And that is it for our video today. I will see you on the next one.